So now that we're done with the forward propagation, with the backward propagation, we'll also apply the same sort of idea that we've done before, but this algorithm is going to change a little bit because we're going to have, once again, three different weight matrices. So we have WY, WH, and WX. So when calculating the partial of the error with respect to the weights, we're going to have to take into account that we have three different weights. So we're going to do that same calculation of that same partial derivative with each weight separately and then add them all together at the end. So this kind of expands the algorithm a lot more, but some of the steps should be kind of familiar. Some of them will kind of change, which we'll see as we go through them mathematically. But just going through the weights one by one, we can break them down into parts. So we can first calculate the error with respect to the output weight, and then the error with respect to the hidden layer weight, and then the error with respect to the input weight. And just illustrating that, like, we'll work with the same way where we are trying to break it down with the chain rule. So here's our summation of the errors, and we're going to break it down one by one. So starting with the output weights, we're going to start breaking down the chain rule of the output weight. So just illustrating that on the diagram itself, we can see that here's our error. We're going to connect the error to the output itself, the activation of the output, and then the output to the pre-activation of the output, and then the pre-activation to WY that we want. So there will be just three steps in this chain rule. So it's pretty straightforward, and it is actually like very familiar to what we've done before, since we are using softmax function as the output activation. We can see like a lot of familiar parts here. So we're just breaking them down. We're going to have E over Y, and then Y over Z, Z of Y, and then Z of Y over W of Y. We're going to sum this. Once again, this is going to show up in basically every step, but we're going to sum this over all of the time steps. So from t equals 1 to capital T, which should be all of the time steps, or however many input words that we have, for example. So breaking this down, or this chain rule down, these first two parts we're already kind of familiar with. So again, we're working with the softmax function, and we've already calculated this for the softmax before with the multi-class classification. So this E over Y and Y over Z is just Y minus L of T. Or in the multi-class classification, we took that as Y minus T, where T is our target. Here L is our target output. But we can just simply, we don't necessarily have to go through that proof again. We can just simply plug in that part once again, that these two first components of the chain rule is just going to be Y minus the target. And then the last part, Z of Y over WY, is just going to be the partial derivative of Z of Y with respect to WY, so it will just be H of T. This will go, and then it will be H of T, and then the bias is just 0. So yeah, putting all those parts together, we have this simple equation that we've already kind of seen before. It's very similar to the partial derivative of the outputs to the weights in the other lectures. So it's just going to be Y minus L of T, which is the predicted minus the target, times H of T this time. And for the bias, if we want to do the same thing with the bias is just going to be like doing the partial derivative of this with respect to the bias instead of the weight down here. So bias is going to turn into 1 times Y minus L. That's it. So pretty simple. In the lecture, the doctor also does this, but in a different sort of ordering. So going down here to the equation, partial E over partial WY. It's the same idea, but the doctor kind of doesn't expand the chain rule as far. He only writes E over Z of Y, and then Z of Y over WY, and then substitutes this with sigma, or sorry, delta Y. And delta Y above he defined as delta Y equals E over Z of Y, and E over Z of Y is E over Y times Y over Z. So it's this exact same chain rule here, but he kind of wrote it in a different ordering and substituted this part, these two components, with delta y. And then it's going to be the exact same thing, where it's y minus L of t. So similar to the other lectures, delta y, it is just E over Z. Whatever Z that we are at, whatever pre-activation that we are at, it is going to be that total chain rule of that. And we've done that before in previous lectures. The doctor is doing that again in this lecture too. It's not necessarily to do it that way. We can just expand the chain rule as it is, and we'll get the same result in the end. But yeah, same thing here, where delta y times h of t, and then delta y for the bias. That's it. So that's the output. Very familiar to what we've taken before. And it's basically the exact same thing, but it kind of gets a lot more complicated with the hidden states. So now that we're done with one part of the error, moving on to the next one for the hidden states, we can illustrate this again through the diagram first and then go through it mathematically. But the idea of it is similar. So we're going to go from the error to the output, and then from the output to the pre-activation, and from the pre-activation to the hidden state itself, and then from the hidden state itself we can go to its own pre-activation, which is going to be Z of H, and then from Z of H we can get this W of H, right? So it's just going to be this simple sequence, but this won't be the end of our chain rule. If we take a look at the diagram, we can notice that there is a WH here almost directly connected to this. Not entirely directly, but we can also create a chain rule from this hidden state, h of t plus 1, to the hidden state before it, and then from the hidden state before it, we can also get to WH. So there is a connection between this hidden state and the WH from the hidden state before it as well. And this is the important part of the whole chain rule here in the hidden states, is that the hidden states depend on each other. This is the whole idea of the memory, is that all of the hidden states are connected. And as a consequence of that, all of the hidden states impact each other through this weight matrix that they all share. So whenever we calculate the effects of the weight matrix, we can't just calculate from one hidden state. We have to calculate for that hidden state and all the one beforehand. So it will be a lot clearer going through it step by step, but the basic idea of it is that since all of these are connected together, we have to create a chain rule from here all the way to the end. So going through that step by step, mathematically, we can see that the partial of the error over partial of WH will be the same steps. So E over Y, Y over Z, ZY, ZY over H of T this time, and then H of T over Z of H, and Z of H over W of H. So this was the step just in this input, going all the way down to Z of H to this output matrix here, or weight matrix, sorry. But this is not enough, or there are other paths that we have to consider, where this is another way of visualizing it. All of the hidden states depend on each other. This final hidden state here, for example, they're using different notation from us, but it's the same idea. All of these hidden states, 4 depends on 3, 3 depends on 2, 2 depends on 1, 1 depends on 0. And 0 is this beginning, starting state, where we just consider it a constant. But all of these are connected to the weight matrix, the same exact weight matrix. So since we are trying to find the effects of this weight matrix according to the error for each one, we're going to have to calculate the dependency between this and this, this and this, this and this, and add that to our chain rule. So our chain rule now expands. If we are at time steps t, so with this hidden state, if we are at h of t, we're going to have to look back and go to h of t minus 1, like in this diagram, for example, or in the diagram that we have in the book as well. The doctor kind of goes through it below as well, but in this diagram, if we are h of t, we're going to have to go back and look at h of t minus 1 as well and add it to the chain rule. So we're going to expand this chain rule. So now it becomes, instead of just zy to h of t, and then h of t to z of h, and then z of h to wh, we're going to have to add this in between. So this is what it will look like when we're at h of t, but no matter what point we are in, and no matter what time step we are in, we're going to have to look back to all of the time steps before us, to all of the hidden states before us. So in general, doing a summation, we're going to have the same first three components, but once we get to h of t, we have to be looking at h of t with respect to h of k, and h of k with respect to its own z of h, and z of h with respect to wh. So we're going to have this summation from k equals 1 to t. So if we're at time step 4, for example, we're going to look at 4 to 3, 3 to 2, 2 to 1. And some resources say like 1 to 1, but that's just going to be 1 in the end. But yeah, the idea is that all of these hidden states are connected together. So, and all of them are connected to the WH as well, which is what we want in the end. We want to find the relation between the error and WH. So this becomes, as we expand this a lot more, we can notice that this is just a product in the chain rule, that we are multiplying the same thing over and over again. It's just like with that example for 4, 4 over 3, 3 over 2, 2 over 1, and such. So we can substitute this part with a product rule. So starting from k, whatever k we're at, all the way to t minus 1, we're going to do hj plus 1 over h of j. And it will work out to be the exact same. But we can see how this kind of turns to a product of h of t over h of t minus 1, ht minus 1 over ht minus 2, and so on until we reach k, whatever k we're at right now. And this was all for just one single time step. We are going to have to do that for all the different time steps. So at this time step, for example, ht minus 1, we're going to calculate the error to it, and then look at the time step before. And then moving on to the next step, we're going to calculate this error, and moving behind it, calculating the relation, and then moving behind it as well, calculating the relation, and so on and so forth. So once again, this summation shows up from t to capital T, where we're going to do this over all of the different time steps that we have. But this will be basically the final equation that we have. It is super long and kind of convoluted, but we just need to know like how we got to this point. But this product, while it seems kind of simplified, it introduces a lot of issues. So we can kind of visualize it first and then go through it mathematically as a proof. But this is our origin, or the reason for our vanishing gradient and exploding gradient, like problem in RNNs in general. This problem exists in all neural networks in general, but it is very apparent in RNNs because of how deep they can get with the unfolding. But if we look at this example here, going through the forward propagation first, we have an input sequence of words in the sentence. She kicked the ball right into the blank. And we want to, for example, let the model predict the next word. So going through it one by one, at the start, the only word we have is going to be she. And then as we keep going, we're going to keep propagating the weight of that word to the next one. So she kicked is going to contain the effects of the first one with the effects of the input going in, with the weight of this parameter going in, and then so on and so forth. So as we keep going, we're going to keep propagating and multiplying all of these weights together, since that's the whole idea of it. All of the hidden states depend on the one before that as well. So as we keep propagating and as we keep multiplying the weights together, we're going to eventually notice that the weights of the beginning sequence of the first few words in that sequence will kind of be irrelevant compared to the ones later. Since we are multiplying so many numbers together, it will either expand by a lot or shrink by a lot. And we can kind of, like, if we consider, for example, a number like each weight has a static number of 3, for example. At the very beginning, the weight is going to be 3. And just consider as the weight as its only output. Obviously, it's not going to be like this. It's going to be a lot more complex, but just for the sake of the example, if the weight here is 3 and every single WH is 3, every single time we're going to be multiplying by 3. So 3 times 3 is going to be 9. So we still have the effects of the first one here, but afterwards we're going to have 3 by 3, it's going to be 27, and we can see that starting to like shrink a little bit, how we're growing not exponentially, but in a very fast rate. Times another 3, 81, and we keep growing, so on and so on and so on. So we can see how the numbers will explode or shrink. If the numbers are smaller than 1 or a lot smaller, then it will slowly converge to a very, very, very small number. And that will cause a problem in the backpropagation, because we can't really associate properly which error with which weight or which time step, if that makes sense. So at the very beginning, we have this huge number from all of this propagation of all of the input sequence, but as we keep going back and back, that effect kind of decreases, and we won't, by the time we reach the beginning of the sequence, we won't necessarily know if the effect was from this sequence here or this part of the sequence or at the end. It will make a lot more sense mathematically, but just through the diagram we can kind of see how this propagation of the weights, us multiplying all of these hidden states together, kind of reduces the effect of the first one. This is why we use LSTMs at the end, and why it kind of tries to fix that problem of the vanishing gradient. It all originates from this problem of this product, or this propagation of the weights multiplying together. So going through it more concretely, mathematically, we have this product, h of j plus 1 over h of j. We want to try to break that down. So that partial derivative is actually a vector over a vector. Each hidden state is going to give us an output of a vector, since our input is also going to be a vector. So we've kind of seen this before, but with that Jacobian matrix, we, instead of having just a scalar as an output for that vector, we're going to have a matrix. We can look at it through this example. They use different notation. We don't have to focus that much on the notation, just the idea of it, and then connect it to the ones that we have in the book. But the idea is that we have, for one part of this product, if we, for example, we're going to take s of j over s of j minus 1, and s of j is basically the same as h of j. So taking one part of this product and doing the partial derivative of it, we're going to do the chain rule. So s of j, which is h, over a of j, which is going to be the z, or the pre-activation, times a of j over s of j minus 1, the one before it. And we can kind of see this here as well, where a of j is the weight times the pre-activation, or the previous h, and then plus the bias, and s of j that we are at right now is going to be the tan of that, the same exact concept. So going through this, we can see how, as like a Jacobian matrix, we're going to basically just look at the diagonals themselves. The other values where the indexes aren't equal to each other will turn out to be 0, and the only values that we'll have remaining are the diagonals. So calculating this part of the chain rule, this sj over aj, will give us this Jacobian matrix, which is just going to be this diagonal. So this diagonal, once again, s of j is this equation. So getting the derivative of this is just the derivative of the tan. So this value, the sigma derivative of a of j. So going back to the chain rule, this first component is the diagonal that we calculate from the Jacobian, and this component, a of j over s of j minus 1, if you go back to the equation, a of j is the weight times sj plus b. If we do the derivative of this with respect to sj, we're going to have the weight remaining, so sj is going to go, and b is just a constant since we're not doing derivative with respect to it, so we're going to have the weight remaining. So this part is the diagonal, this part is the weight. It's a little bit convoluted. We don't necessarily have to know these details, but this is the details that the doctor kind of leaves out in the book. And this is how the doctor reaches the point of here. So going from this chain rule or this product to this, that is what we've basically done here. So like connecting it to our own values, what we just did was h of j plus 1 over h of j, and try to break down the chain rule of that, which will just be the diagonal of that Jacobian matrix, where this phi, like the doctor wrote, is going to be the tan h function, and then here it's supposed to be z, it's not supposed to be h, but this phi in z of h times wh. And then we get through more proof, like this is a linear algebra part, but we want to try to find the magnitude of that diagonal. So trying to find the magnitude of a matrix, or magnitude of these two multiplied together, we can do that through getting the norm of each side of the equation. So getting the norm for each side will be this norm equals this times this. So in linear algebra, if we have C equals norm of A times B, we can then say that the norm of C is less than or equal to the norm of A times the norm of B. So this is basically what they've done here. We don't need to know the proof of this, we don't need to know why they did this necessarily. They're just trying to prove the fact that this value can have a maximum and a minimum. So when looking at each value on its own, down here, the diagonal of this derivative of tan is going to just be like according to this function here. The tangent function has a maximum of 1 and a minimum of 1 normally, and when we derive it, it's going to have, like this is going to be the look of it, this is the shape of it, it's going to have a maximum of 1 and a minimum of 0. So this part of the equation, we can say it's going to have a maximum of 1 at most. There's never going to be a value here in this part that will be greater than 1. Most of the time it will actually be closer to 0 more than anything. And this part, this completely depends on the weights, which are random, like we don't necessarily set them. But this part will always be less than 1. So if we give each one a symbol and substitute them for a symbol, we substitute the first part as gamma and the second part as lambda. We do this to kind of show that if this gamma and lambda are really small, we can see how that will lead to a vanishing gradient. And if it's really big, you can see how it'll lead to an exploding gradient. So for example, if we have our weights set as a random number, like 50, which is very high, but if we have our weight as 50, for example, and our gamma as at some point 0.5 at this specific time step. So we can say that at this time step, this value of S of j over S of j minus 1, which are the hidden states, is going to be less than or equal to 25. Or we can basically say that it's equal to 25 at this specific time step. We're going to do this over all of the other time steps. So coming down here, we can see that over all of the time steps, we're going to apply the same thing with the product rule. This is the product rule that we had at the very beginning. So this exact same thing will apply to the others. And since we are multiplying them all together, we can just summarize them through this product rule. And we can basically say, like we can summarize this product rule in this form. Since we are just multiplying together the same exact thing, it's just going to be gamma times lambda to the power of t minus k, where t minus k is basically just the number we have. T is the maximum number of time steps, and k is our starting point. So for example, if our input sequence is made up of 20 words, this will be like 20 minus 1, which would be like 19. In a bigger example, like in a more realistic example, we can have a sequence of like 1,000 words or like 500 words or whatever. So if we keep going with our example where we said gamma was 0.5 and lambda was 50, so we have 25 to the power of 500, for example. This is a very, very big number. Usually it will be a lot smaller than this, but if we have a number like this, it is going to explode exponentially. A more realistic number would be something like 1.02 to the power of 500. So even with such a small number like this, we can see that the gradient will start exploding. And this is quite a small input sequence. We can have an input sequence of 5,000 letters, 5,000 words, and we can see how the gradient will start exploding beyond that. But what if it's less than that? What if it's a realistic example as well would be like 0.92 to the power of 5,000. We can see how this will eventually go towards 0, and the gradient will eventually vanish. So we will have a problem with our training at the end. So the whole idea of it is that this multiplication will result in either a gradient exploding or a gradient vanishing because of how big the input sequences are. This is just a consequence of the model itself being sort of interconnected together in such a way that we are multiplying all of the input sequences together, all of the hidden states together. So this is the main idea or the main problem of the vanishing sequence, is that we are going to have this issue where if our gamma and lambda are greater than 1, we are going to have an exploding gradient where it's just going to be massive to the point where we are taking these giant steps, like thinking back to gradient descent, we're taking a lot of really big steps and not really reaching an accurate minimum. And if it is less than 1, then we are going to eventually reach a point where the gradient is 0 and the model isn't going to learn anything. So that is the whole idea of it. We don't necessarily have to know the proof. That's why the lecture left all of it out. I thought it would be maybe helpful if like we could see what was actually going on. But yeah, because of the nature of the tan h function that we saw here, usually the weights will be moderate, and usually this function will almost always be around here, somewhere in the middle. So it is almost always going to be less than 1. So if the weights were a moderate value and the gamma were like a value of like 0.4 or something, then it would be less than 1. It would kind of force the whole equation to be less than 1. It would be raised to a really big power, and then it would cause, once again, the problem of vanishing gradient. So that is the big issue that we have with RNNs. We fix this with LSTMs, which we'll look at later. But yeah, that is the whole idea or summary of it, is that depending on what weights we have, if our weights are really, really big, like in the example that we had, if our weights are 50, then we'll have a huge exploding gradient problem. If the weights are moderate, we'll usually have a vanishing gradient problem because the gamma itself, because of the tan h function, will be less than 1 and it will eventually just vanish to 0. So that is the idea of it. But going back to the hidden layer itself, or the hidden weights themselves, we'll calculate them in the way that we saw earlier. So going back up here, through this summation we can calculate the hidden weights. In the book, the doctor once again does this through delta h. So he defines it in the same way through delta partial e over partial z, and partial zh over partial wh, and then wx down here. He does the same thing for both. because both can kind of rely on the same exact calculation. And the way he defines delta H is once again E over ZH. So what paths exactly do we have going to ZH? We have from the loss here, we can go from this output, or rather we should take it from down here, but from this we can go here, and we can go here, and then we can go down to ZH over here. But we also have to consider that going backwards through here, through this arrow, like we can follow the red arrows, this hidden state had an influence from ZH over here. So from the hidden state ahead, we're going to be able to also access this ZH. So that's the steps that the doctor was following to get this sigma through the substitution. So E over H and H over Z, we're going to have our own outputs. So E over Z of Y and Z of Y over H. That's going to be our own output at the time step that we're at right now. And there's also going to be the time step ahead of us. So the time step ahead of us, the Z of H plus 1 here, was influenced by this H of T, since that ZH plus 1 was a result of this weight times this hidden state plus a bias. So both of them have an effect, and both of them will contribute to this delta. So that is why we have this addition here, and we can just do more substitution, where this part we've already calculated as delta of y, and this part zy over h of t. If we go back to z of y, if we do z of y with respect to h of t is going to go, we're left with wy. And obviously the bias is not going to be there, it's just going to be a constant. So that is why we have delta y times wy. And same thing here, we're going to have delta h, but of t of plus 1 times wh. Once again, z of h with respect to h of t minus 1 will be wh. So come back down, we'll have wh at the end. And the derivative of the tan function, which was partial of h of t with respect to z of h, is just going to be 1 minus tan h squared of z of h. So we can follow the sigma, or once again, the delta route that the doctor did, or we can just do the big summation at the end. Both will once again give the same results, but the same thing applies to the inputs. That's why the doctor kind of did them both in one go, where from the hidden state, we're also going to go just one extra step to the input. Instead of going back to another hidden state, we're going to go down to the input that we have. So we're simply going to add this step instead of going to WH. Z of H already has the input connected to it, so we're just going to say Z of H to WX, and then multiply that by the X instead of the H. So that is the basic idea of it, of the RNNs. It is a lot, especially when it comes to the hidden states, but I think we just have to understand the idea of how we get each error on its own, and then what exactly causes this vanishing gradient. This product of all of the hidden states connected together creates this big issue where we have to consider all of the hidden states that come before us as well. And because of that multiplication, both mathematically and just intuitively, we can clearly see that there's going to be a huge problem when the input sequence gets very, very, very large. And this applies to all neural networks, where if we had a neural network with 5,000 layers, then this same problem would apply, where we have this vanishing gradient, and the first few layers will have basically a negligible impact on the output at the end. We won't be able to really learn anything from it. So yeah, that is basically all of the RNN. Going on to the LSTM, the basic idea of it is that instead of just having all of the hidden states directly connected to each other, we're going to put a lot of these gates between the hidden states, and then every single time step, we are going to predict, or not predict, but we are going to choose whether to forget certain information and remember other information. So we're going to have these gates be a sort of intermediate layer between all of the hidden states and the actual output that we have. So between each hidden state, or between each time step and the other, there's going to be this module, of all of these gates together. So here, just from the diagram itself, we have our input going in with the hidden states previously, and then we're going to decide based on the gates what goes into the actual hidden states and what goes into our cell state. So this cell state is kind of the first gate that we have. This whole cell state we can think of as our new memory component. This is where we decide what exactly will be saved and what exactly will be remembered and what won't. So depending on the inputs that go into this, we're going to decide that. So just going through them one by one through the gates, they're all listed down here already, but we can see I is the input gate, F is the forget gate, O is the output gate, C is the memory cell, that is the main component controlling the memory, and H is the hidden state, the one that goes towards the next one. So instead of just the hidden state being the only memory component that we have, the idea is that our C, our cell state, is going to be our main memory component. It will depend on the hidden state, which we can see in the equation here. So C kind of takes the job of the previous hidden state. So it will be the one taking control of the previous hidden state. It is taking the job of the previous hidden state and also our input going in, the X going in. But going through these one by one, so all of these have this non-linearity where most of them are actually sigmoid this time instead of tan H. The C is going to remain tan H since it is taking the same job as H of T before, but all of these are going to be sigmoid functions instead of just the tan H function, because all of these gates, we kind of want them to have the functionality of turning on or off. So especially, like, this will be clear with the forget gate. The forget gate will decide whether we take in the previous information that we have or not. If we don't want to, we can simply turn this forget gate on and nothing will go by here. So we can activate this forget gate to where the sigmoid function can give us an output of 1 or 0. We can activate it to give us this output of 0, and it will forget anything from the state beforehand. So as an output here, this forget gate, will either give us a 0 or a value close to 0, or a 1, like somewhere in between, or a 1. So if it gave us a 0, it will go into the cell state, or this cell memory that we can think of here, and it will basically just nullify all of it. Since this is a multiplication, a crosswise multiplication, 0 times anything will be 0, so there will be basically nothing going through here. But it won't just be nothing, like we can move on to the next gates. So if the forget gate cancels out all of the previous input, the input gate will will enable us to remember it and also look at the new input. This is also really clear in the equations too, where the input gate is looking at the X as well. The forget gate does as well, but each of them have their own weights. We don't necessarily need to know how they set their values or what exactly the weights, how they optimize them, but we just need to know the functionalities of each one and how it helps us prevent the problem of vanishing gradients and exploding gradients. But the idea of it for the input gate is just that it will take the previous hidden state and the incoming input and then calculate that along with the C or cell state that we have also calculated through the tan H. So there will be crosswise multiplication and that will be added on to the cell state. And then the output also works in the same sort of way, where the output will be crosswise multiplication of whatever's on the cell state with the input going in, and that will be the new hidden state. It's a bit convoluted, but all we really need to know is that we are now controlling the flow of information. We get to decide, or the model will get to learn what information it can erase, what information it can remember, and what information it can propagate forwards. So we won't have this direct multiplication between all of the hidden states with each other. Like, we can drop a lot of the hidden states and only propagate the information that we need. And we can look at this mathematically as well, how it will fix it, where when we start looking at all of the equations, the main equation we have is the cell state equation here, C of t. So when we do the derivative of that, this is the big problem that we had before, where, once again, this is basically the equivalent of h of t. So when we were doing the product of h of t over h of t minus 1, and doing the partial derivatives of each one, we had this big issue of the vanishing gradient due to the Jacobian matrix and due to having this really, really, really big power applied on the values that we get. So how does this fix it? We'll look at one single example as well. When we do the derivative of this function, the C of t is going to be made up of f of t, the forget gate, times C of t minus 1, plus the input times C of t. We can look back here as well, but you can see how C of t is going to be the result of this plus the result of this. And the big point is this plus. This plus over here. This is what helps us prevent it. So we don't necessarily have to go through the derivative in detail, but this is derivative of two functions multiplying each other. So derivative of the first one times the second, plus the derivative of the second one times the first, and the other side as well is going to be the same thing. But the important point is that at the end, after getting all of the derivatives here, we are gonna, instead of having just multiplications into each other, and like in the hidden state, we got that through the Jacobian matrix, where we got these values all, or they're not zeros, but just the values here, all of them are being multiplied together in a diagonal, and that product being a huge power at the end, where we get t minus k. Here instead, we're going to have this part of the equation plus this part of the equation plus this part of the equation plus this part of the equation. The important part is this addition, this plus. This plus enables us to have more freedom in terms of vanishing or exploding gradients. If in any calculation, any of these numbers are huge numbers, like for example, if this, for instance, was 500, and this number was like a small number, like 0 point something, this one was 0 point something, this one was 0 point something, it won't get multiplied into all of it and increase all of it. It won't be 500 times a bunch of numbers. It will just be 500 plus 0.1 plus 0.1 plus 0.1. If this was if they were a lot bigger, if this was a lot bigger as well, if this was 2, for example, and this was 3, and this was 4, then the number would be a lot bigger. But since it's just an addition, it won't really affect that. The same thing on the other side. If this was, we can still have a problem of exploding gradients, and we can see why, but we kind of eliminate the problem of vanishing gradients, where if this was a 0, but this was some number, and this was some number, and this was some number, we don't have this scenario of having a really small number or a 0 kind of shrinking down a lot of other numbers. Each number is going to give its own input to the gradient in the end. So every gate is responsible for its own gradient. It won't affect the total gradient in the end and kind of explode it or vanish it. There might be a problem at a single time step where it might not learn something, or it might forget something, which is on purpose, but it won't affect the other gradients in a way. So we kind of reduce that vanishing gradient by a lot. The worst case scenario is where we have a lot of them being close to 0, but even in that scenario where this is like 0.1, for example, this is 0.2, 0.3, this is 0.4, even in that example, the number will still grow and become closer to 1, for example. And at the next time step, it can keep growing and actually becoming a proper gradient that we can work with. It won't ever reach this vanishing point where we don't learn anything anymore. So the whole idea of it is that the splitting all of the hidden states into all of these gates gives us a lot more control over what we forget and what we don't, and it also has this consequence or this benefit to us of letting each gate be responsible for its own gradient. So that is how we kind of prevent the vanishing gradient problem in LSTMs. There is still an exploding gradient problem where a number can be way too big, and since you're adding a really big number with a bunch of small ones, it will obviously have a lot more impact. But that is what the doctor talks about here, where we can kind of use a gradient clipping. So the whole idea of gradients is that we want to know the direction that we take. So when we have a loss chart like this, for example, or a cost function like this, we want to know the gradients mainly for the direction. Like if we are at this point, we want to know, okay, go down in this direction by a certain amount. We don't necessarily need to know the amount itself. So if the amount is way too big, the magnitude is like plus 500, which is way, way too big. Like this is not that realistic of an example, but if it is plus 500, we can clip it. We can say, as a, like whatever gradient you get at each layer, bring it down between the value of negative 1 and 1, for example. So all we care about really is the sign. This will mean that we take a lot smaller steps, obviously, but it kind of helps us prevent that problem of the gradient exploding. So at every single time step, you're going to clip the gradient. You're going to say, like, the gradient cannot go beyond 1 and cannot go beyond negative 1. Whatever it may be, if it goes here to negative 5, you'll bring it back to negative 1. So it'll be a negative gradient still. You know the direction, but the magnitude will be a lot smaller. So that is how we can kind of defeat gradient exploding. And gradient vanishing, we've kind of already defeated through this addition symbol. Through, instead of having this big product, we eliminate the product, and we're going to have the gates that act as an intermediate layer, and all of the gates are responsible for their own gradients, their own weights. And in that sense, we can kind of defeat the problem of vanishing gradients. So yeah, that is the whole lecture basically.